Being able to move and transform stresses is kind of cool and everything, but in the big picture, are they really that useful? It's kind of like finding that torsional stress in the middle of the beam. Yeah, great, I can do it, but what I really care about is what's going on at the outside of the beam. Why? Because if things are going to fail, that's what we're going to be looking at. Engineers are most interested in what the minimum and maximum stresses are because that's where things are going to break. That's where the interesting stuff is going to happen. Same thing with plane stresses. So what I need to do is I need to take those equations and I need to figure out how do I rotate them to get the maximum stress. And so what we do is, just like with any equation, we can sit there, well, I can maximize an equation if I look at the derivative. So if I look at, and actually this should be, if I take that normal stress equation and differentiate it with respect to theta, I should get 0. And so what I can do from that is I can solve this equation, and then I can define what theta I need to rotate to get the maximum stresses. And we're going to call that theta sub p the principal axis. So the principal axis is going to be the amount that we have to rotate something to get the maximum solution. And that's going to give us our principal stresses because we're going to have along those principal axis stresses that are going to be maximized. I've got two different ways that I can solve this. The first way would be to use this equation. I can go back, plug all this stuff in, and generate my principal stress equation and my principal axis equation. I can also do it via graphs, and I'll get the exact same answer. So what I'm going to do is, let's actually look at it on the graph. So if I take those previous equations that I've got, that sigma x prime, sigma y prime, tau x prime, y prime, I can put it together and I can combine it into an equation that would be the exact same equation for a circle. And that would come out to be sigma x prime minus sigma average. I take all of that and I square it, plus tau xy squared is going to equal r squared. There's a lot of algebra involved in that. I don't really care that you can work through it because you'll never do it again beyond just deriving these equations. So sigma average is going to be what? Well, that's going to be our original stresses divided by 2. Now, notice these are the originals, not the transformed. And then what's our R going to be? Well, R is going to be the difference between those two stresses squared plus tau xy, and that's the square root of everything. Once again, remember, all these stresses are the normal ones. And so what's going to happen is, well, we can draw a circle off that. So here's our center of our circle. It's going to be the average. And then our radius, and we take the radius and we swoop it around a lot. Later, when we talk about something called Moore's circle, we'll be playing around a lot with this, but not right now. Right now, we're just going to stick with our equations. Okay, and so that's what we end up getting. So what do I do? So the principal stresses occur on the principal planes of stress with 0 shearing stress. What does that mean? Well, that means I'm looking at points A and B, because points A and B are where we're going to maximize that normal stress. And so, once again, how do we calculate that? Well, this is when we go back to either we do it via that equation that we've got, or I take a look at where I can maximize and minimize my equation. So where's the maximum n going to be? And I'm sorry, up here these are primes. Well, my maximum and minimum are going to be where I have no shear stress on my equation. So what I'm going to be left with is my maximum and minimum, which for principal stresses, we call them 1 and 2. Because 1 and 2 is you get your first principal stress, you get your second principal stress. And so what that's going to be, it's going to be the average stress. So we're starting right here at point C. And so A, well, A is going to be the average plus the radius. B, the minimum, is going to be the average minus the radius. So plus or minus our radius of our circle. sigma x minus sigma y divided by 2, all of that squared plus the initial shear stress. And there we go. So that gets us our positive and our negative. Well, not really our positive or negative, our first and our second. They can be positive or negative. It's just in this case, that's what we have. Now we have two solutions for what the angle is, and we can work that out with geometry, or we can go back to, once again, just plugging in our solution for d sigma prime d theta is going to be 0, and what we'll end up with is our equation for tangent 2 times theta p is going to be equal to twice the shear stress over sigma x minus sigma y. Now, remember, we've got two solutions for theta p because they are 90 degrees apart. And so you're going to have theta principal 1, and then you'll have theta principal 2, which is just going to be theta principal 1 plus 90 degrees. And so that is where our maximum stresses are. So once again, yeah, it's great that we can rotate it and find out what it's going to be at any place, but what we're looking for most of the time is what is the maximum amount? What is the highest amount? And that's going to be our principal stresses. That is going to give us our highest normal stress. But we could want to know what the maximum shearing stress is, because we have certain things that will fail in a shearing form. So where's the maximum shearing stress going to be? Well, if we look at the little equation that we put together for the circle, there's my average stress. My maximum shearing stress is going to be at the exact same point. Because why? Because we have the average plus the radius. And so if I add anything to the radius, if I add anything to that, it's going to shift over a little bit, and it's going to bring that shearing stress down. So what I want to do is I want to find it exactly at the average, and that's where it's going to maximize my shear stress. So my maximum shear stress is going to be equal to what my radius is. Stress x, stress y divided by 2 squared plus tau xy squared. Let me fix that there. But we have two stresses because they're going to be offset. So your maximum shear stress is actually a plus or a minus, because we will have a positive, negative stress. The shear stresses are always going to be the exact same. So typically, you'll see when they do what's the maximum shear stress, if it was positive 90 KSI, negative 90 KSI, they would just say that it's 90 KSI, because really the sign doesn't matter for shear stress. So typically, you won't even see this plus or minus. You'll just see there's the maximum shear stress. Because unlike normal stresses, there really isn't a positive and negative shear stress, because it just is, because it's in plane. Where normal stress is positive and negative, talk about tension and compression, shear stress is just that value. So that would be the max shear stress. In fact, if you wanted to really technically be correct, this would be the max in plane shear stress. That becomes important when you're looking at three-dimensional shear stress, three-dimensional transformations. Max in plane shear stress. And we can find that angle, so tangent theta s, and we'll say theta s, we're going to define that, we'll call that the shear angle, and that's the angle that you need to move it to, or the principal shear angle, the angle that you need to move it to get the maximum shear stress, and that's going to be negative xy minus sigma y over 2 tau xy. And so that's how you would find it. And so you've got those two angles, those two stresses separated by a 90-degree angle. So there's a maximum in-plane shear stress. There is how to calculate that principal shear angle. So these equations make transformations from the last lecture. Transformations really easy. These ones are the important ones, though, because you're going to want to know what is the maximum shear stress for a state of stress? What is the maximum principal stress for a state of stress? Because you really need to know this information for when you're doing design, because maximum's where things happen.